Good morning, good morning, or afternoon. Just checking out the audio right now, making sure we got that situated. That should be good. Welcome back. I know it's been a while, holidays and whatnot, but here we are, ready to get back to it. Lastly, we had left off with our first training run. Um, we were able to, let me see here, hop into our virtual environment first. Back open bin. We're gonna activate or source the activate script so that we can get into our virtual environment like always. Um, and then from here we had our source code, and this is where we were in our training.py, and that's producing our num classes. That's showing our num classes here. Hold on. Shoot. Music sounds kind of loud for me. Let me put that on. Alright. There is. That's better. Two two classes as we had before, and we can see the true label was predicted inside of the predicted label index, and then it is leaning towards your cornerback with a higher truth score. Well, the logits. Um, so the next thing that we're most likely, not most likely, but definitely going to need to add is a way to alter the weights and deal with cross entropy loss functions. So let's start looking at that specifically, how we're going to handle the loss function first. Um, the this was some output we had prior just to see what's coming out of the batch, which is going to be 5 for that batch size on the data loader from the training data set, which was still pointing to the training directory that's going back to DIRs or Wonder to train data and performing the transformer Bumblebee, which is resizing everything to the ResNet 18 model specifications. Uh, from there, we also deal with the normalization of the RGB inputs to, from what I understand, is to function within the same grid as the ResNet. Um, from there, we instantiate a model object using the ResNet 18 and the default weights of that model, weight specifically of ImageNet 1K v1. From there, we're creating a final layer That's going to be the output layer in regards to whether it's going to be a cornerback or a wide receiver. And then we are creating that neural net linear final layer, inputting the weighted inputs that should be coming from what's already considered to be the ResNet 18's fc.in features. So how many weighted inputs are normally coming in from the model? We still want to keep that because we're using that as the base model. And then the output is going to be outer num classes that we're pulling from the length of training data.classes. After that, we push over the model to our device, which is going to be our CPU, which we found here. CUDA, if torch.cuda is available, is not found, so we're going to use CPU. From there, you're getting the X and Y from the next iteration of the training data loader. We'll send the X to the device, which is going to be the batch of size 5. And then the Y is the outputs, the true label output of each input. After that, we're working without a gradient descent, and we're getting the logits and prediction of, you get the logits of the model and then the prediction of whether it's 0 or 1, and then we're outputting the y equals 0, y0. I see. We're outputting the first instance of this array of the y's that are being output. This could be I as 1, and we would get technically different outputs. But do we even know which one's being tested? No, because we have no specification on if this should be shuffled. I believe it starts with shuffle true, if I'm not mistaken. After that, still, like I said, batch size, you're getting a float from your resolution because the logits are going to be in decimal. And then you have your value range of, what was the value range again? Is it the logits? I think, yeah, these are, no, these are not the logits. What are the value ranges again? Each number X. Okay, so the line is printing the minimum and maximum values in your input tensor X. X dot min item minus string X max. Each number in X is one channel value for one pixel after preprocessing. Is that true? Because this X is coming from the data loader itself. Yep, simple. Integer 0, 1. Yep. 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 We went over all this already. What the data set says what the data set says the image actually is, what the model thinks it is going to be the predicted label. Raw scores are your logits. You get your output, which we have right here already. So then the batch size, sending checks on inputs, 5 on the batch size, RGB, 224 by 224 resolution. You're getting float for your gradients, your convolutional neural networks, and then min-max pixel values after normalization. Expected range. Oh, okay. So that's coming from, I see. That's coming from the normalization. So everything should technically be around there, around the same, regardless of how many times I run it. Let's try this again. Okay, so definitely a different label because you're getting the true label index is different. And the predicted label, it predicts it perfectly fine. Different logics here, but this part is the same because of the normalization. Gotcha. Okay, so now after that's done, we're going to get our outputs. And just out of curiosity, what will those outputs be if printed? You get, ha ha ha, some funny stuff, whatever that's doing. So it looks like an array. It's your tensor, yeah. And then you have one, two, three, four, five. So in relation to our batch size, and then I'm gonna have to assume these are your logits. But I feel like that wouldn't make much sense now, would it? Model of X equals outputs. Because to have one side continuously negative and other positive means okay. That was just a very lucky run, I guess. So here we have differing answers of which is leaning towards where. Um, to me, these are the logits. Let's just verify though. Outputs, model X, the logits. Yes, those are logics. Awesome, awesome, awesome. So these are logits. Why these are logits? You are using model equals model ResNet 18. Um, your final layer, which should be called FL. What does FC stand for? Um, fully connected layer. Okay. Especially towards the end of the model and a fully connected layer, every neuron in the input layer is connected to every neuron in the subsequent output layer. The final layer is a linear layer. A linear layer computes output. Yep. Shape 5 2 because we have 5 inputs and 2 different possible outputs. Each row equals 1 image. Each column 1 class. Cornerbacks, receivers, larger values, higher confidence relative to the other class. Import. If you want probabilities for inspection only, but do not apply the softmax. Okay. So first, so now we know we can get the logits for a bundle of inputs. So from here, as we learned before, way back when, here, so logits are the raw numbers of probability, while softmax then normalizes logits for use. Right? So in order to, from here, utilize these logics in order for us to define the probabilities within the image, we're going to need to figure out first how to even functionally apply a softmax to our output. So starting there, softmax to output. I really don't like this song. Go. Apply softmax logics like this. Import torch neural network functional as F. We don't have that already, so we have an N, but let's go say import torch dot functional as F, right? And Then we're saying probs, probabilities equals f, that torch and then dot functional dot softmax logits. Dim equals 1. Softmax across the class dimension. I don't know what that means. So let's. One thing I do want to try doing is seeing a bit more variety within my answers, just kind of the minor parts, right? So obviously, apply softmax logics is kind of the overarching step that we're leaning towards. But and going about it this way is relatively straightforward and gives me all the information I need. But as I come to something like this, I want to see it in a bit more of a variety of ways. So only if the class dimension happens to be dimension 1 in the specific tensor you're working with. Let's see. What is in here maybe? For a dimension. Okay, so one dimension is where it's going. Dimension equals 1, softmax across the class dimension. So how is these, what is a class dimension in the first place, right? What is the class dimension? One for first, a distinction. In machine learning, dimensions can be applied in various contexts. Here are two important facets in terms of images, in terms of model learning and feature space. Image dimensions in deep learning, dimensions concerning images often refer to the image's size or shape in three-dimensional images. The height, width, color channel. So, okay, so this is our normalization here. You're resizing, color, RGB, not what we're looking for though. Unsupervised learning. We already know what that is. Okay, so I guess he's not talking about model learning. Model learning. Feature. Okay. Feature dimensions. Here we are. Dimensions also come into play when considering the number of features or variable used to represent each data point. Imagine a model is trying to predict the price of a given house, number of bedrooms, square footage, distance from school on a 3D. Yep, yep. We saw this inside of um, the 3-day, 4-day video that we went over one time, and that looks pretty accurate to the plot, but still not what we're looking for. All right. I tried. Is the axis of a tensor that corresponds to different classes your model can predict. It is a dimension where each position equals one class. The values compete with each other. Your model output state is 5, 2 class dimensions. So for each image, the model outputs two numbers, one per class. So y dim equals 1 for the softmax. Compare classes within the same image. We'll compare different images. Compare classes within the same. Hmm. think of the output like a table like this. Yep, these are the probabilities. Each row is one image, each column is one class. Yep, class dimension is the column direction. There seems to be, there's like one piece of information missing to make it all click. Let's see. Dim equals 0 is doing what versus dim equals 1. We'll see what both sides of the coin are doing specifically, see how they differ and are similar within each other. So 0 is down the rows. Oh, okay. It's just saying which dimension inside of the table to go. It's literally a directional act. Okay. Is the axis of a tensor, as in literally, is it going down? Hold on, I need my paint back. Um, one moment as I find my pen. All right, so all right, so what they're saying is you have your image, and then you have let's see, cornerback or receiver, and then this is gonna be a large one or large zero, large zero for M0, and you can work with your softmax apparently in two different ways. You have your zero or your one, which is gonna say zero. Go down that way and compare this between this, between this, between this. Or you have one, which is gonna change the direction of the axis to it'll compare your values between the two inputs or outputs of your logic of cornerback or receiver. So that is what we're actually doing with the dimension. Now, that being said, I assume it's gonna take the logits and compare which one's bigger or smaller. That's the only reason you would have a comparison, I assume. So you're comparing classes within the same image, yes, because you're going one, which is going to the right rather than down. So each row becomes class 0. Ah, I see. I see. So that's how from the beginning. Oh, we already. Wait, no. Yeah, so logits equals this. So even here, this is where we're specifying the dimensions. Uh, After you get the logits of x, which is going to look like this, you then say the prediction equals logits.arb. So let's take a look at what that looks like in this print prediction. So you get every single prediction for um, the batch, all 5. Logits.argmax. I wonder what this looks like, right? What table this is creating. I assume .argmax. Hold on, let's take a look at this. And before we search, so you have your output, Yep, we did this already. So for each image, compares class scores, convert score cornerback, score receiver to probability of cornerback, probability of receiver. Each row sums to one. I see. Okay. So you're applying a softmax to F, and we're saying F from my memory. Probabilities. Okay. So one step at a time, right? First, your logits are created. So if we print logits, let's go ahead and just get rid of everything else. We print the logits out, you get each row for each image. From here, we also have your list of predictions that correspond with each row. So 0 wins here, 1 wins here, 1 wins here, 1 wins here, 0 wins here. Go. So now we are saying that's cool and all, but we want to apply probabilities to these logits. And the probabilities are going to be equal to using F, this library, essentially this module of Torch neural network functional, applying the softmax to it, using our logits, and then going by a dimension of 1, which is again saying, let's not compare these to each other. We're comparing these to each other. So then now I should be able to print out prob, and it'll give me the output of the logits summing up to 1. And as you can see, cornerback wins out every single one here. Cool. Crossing the possibilities, across the class dimension. Dimension isn't some fancy AI term, it's literally just speaking within the context of a graph. Do not apply softmax before your loss, though, right? So cross entropy loss already applies log softmax internally. Applying softmax twice breaks gradient. So there's no reason for me to actually do this prob.f softmax because first, if I have all the logits, then I could say loss equals criterion equals criterion. Oh, wait, hold on. I need that first. Okay. So criterion equals neural network cross entropy loss. And then we're saying loss equals criterion logits and labels. Labels are coming from the where's labels coming from? Where are they getting labels from? I mean, I guess technically it's here, right? Where I'm printing out the num classes 2, and then this training data classes can technically act as our label. Our labels. Criterion. What is the criterion in the first place, honestly? And what is the neural network cross entropy loss function doing? criterion equals the loss function object. Okay, so it's just an instantiation of that cross entropy loss function. And the job of it is to return one number measuring how wrong the model is. It's really important. So you create the function. Oh, okay. So you create the object of criterion using the cross entropy loss function, or class, really. From there, we want to figure out, well, what's our number, a numeric value for loss. So you take that object that you created, you pass through the logits that you already have from the model and its iteration over the training data loader. And then you are utilizing the labels to determine if it's wrong or right. Um, and then from there, you handle your loss function, you get a numeric value of loss, and then you can update your weights and biases in order to reduce the loss. Um, Now, in order to reduce the loss, the function behind that, you're talking about getting into the derivatives to where the function in the first place, the derivative of it, if we can find where x is 0 on the derivative of the main function, we'll be able to find the slope of where the main function is 0. And then from there, well, we know, okay, if we're either too high, too low, we can find this current slope. And if it's going positive, well, we know we want negative to get into a settled location using gradient descent. So right now we're at just the loss stage to this. So loss labels tell the loss function what the correct answer is. In your case, labels equals y. Um, each label is an integer, right? So your y's are here. So I'm curious. Let's first go ahead and print out y. I just want to see what this looks like. Perfect. So you get the true class labels from the y's, and you could essentially combine this with the logits to see side by side what should have one, right? So all these should have been one, but this one is wrong, this one is wrong, this one is wrong, this one is wrong, this one is right. So we got wait, yeah, yeah. So we got 1 out of 5 correct without training anything, without, the updated of loss. But this in itself, this happening is why we need to then apply the loss function here, swap out labels for y so that it's a one-to-one. First on the tensor for log or for your y is going to be first row for your logits, second, third, etc., etc. We have a criterion, which is going to be the cross entropy loss module, and now we can get the actual loss of this batch after it puts it all together. So you get a output of 0.9472. So we know now that we have the loss value. Apply log softmax to the logits, which happens first, and then you handle whatever calculations is happening inside of that. And then Why do we pass logits to cross entropy loss instead of probabilities? Because the cross entropy loss lid will apply the softmax automatically and turn them into probabilities. Slice would break training. Okay, it does a log softmax into loss. I see. Okay, so flow back from the walk one. If we little logics are passed because they preserve gradient signal and numerical stability. Softmax is deferred to the loss. If you want to continue, the next logical steps are walk one sample through the loss numerically. No. Show how gradients flow back from loss into model FC, which is what we need now at this point. Show how gradients flow back. Right. So this runs through all the convolution layers that have already been trained with inside of this Resonate 18 model. From there, it gets to the final layer, and we have our, or you know what? How many layers do we have? I've just been assuming the fact that this is your final layer because it started with the F, but then realizing now, us going over actually looking it up, this is a fully connected layer. So part of me feels like this might just be a single layer with however many end features and output of how many whatever classes, right? But not necessarily connected to any other layers. Um, Question is, doesn't matter right now. Let's put that on hold. We'll look into that another time. Layers, layer, etc. But right now, step one, one sample, binary case, final layer, linear, z equals the weight times the activation function plus the bias. Output logits for one image. Get to your whatever, you'll get the true label for that. Then you have your cross entropy loss function applied. So forward pass, which owner understands. Step one, linear layer, features A, linear FC, logits of Z, does the loss computational. This is if I change each white. Oh, okay. I see. So it runs the layer, then it essentially tosses it back and says, well, let me try to change the weight slightly and see what happens. P equals to softmax of Z. Gradients of loss. Gradient flow into the weights. So by the chain rule, which we went over in the video. How wrong was that class? This is I want to say the chain rule derivative specifically here. Class K is confidently wrong. The weight gets a big update. Okay. This honestly is some good math that I kind of want to get into. Obviously, I guess not right now, but tomorrow we'll go over all of this math and really start understanding the backwards pass and how it starts updating the weights. What was it? Is that what we're supposed to do today? Oh, that's perfect. So we have the cross entropy loss. We have the cross entropy function, the loss, how to get the loss out of that, the reasoning behind the criterion. This can literally be labeled whatever. It's not important. It is all coming together. The criterion is inputting or taking parameters of the logits that are coming from the model. of whatever pass of the iteration of the training data loader that you're working with. From there, it's comparing to the true labels, handles its own softmax log calculation to give us the final loss. And now, after that, go ahead tomorrow, figure out updating training weights, and we will have essentially everything necessary to start training our AI. So honestly, we got it here a lot sooner than I expected, but I can't complain. That's all I got for today.